All right, so today we're doing Riemann sums, and yesterday we did Riemann sums as well. Yeah, okay, yesterday we did RAM. RAM is rectangular approximation method. Riemann sums is a more generic term for using geometry and using some geometric shapes to find the area under the curve. Okay, so that's going to be kind of the concept that we're fitting in here. This first part of the lesson is not the most exciting thing ever. Okay, it's helping us to understand where this stuff comes from a little bit. We will explore this again after break. It's probably one of the toughest things that I will explain to you. Okay, it gets a little bit funky here, but just remember this a little bit. All right, if I've got this setup right here, anybody remember what that thing is called? This guy? It's sigma. Okay, sigma notation. What do you do when you see sigma notation? You add them up. It's called sigma notation or summation notation. Okay. For example, if you had a problem like this, and I'm going to give it real numbers because I hate when it's not real numbers. Let's say on bottom I said k was equal to 2, and I said 3k, and I'm going to go till 4 just to make life easy. Anybody remember what we do first? I take 2, I plug it in, so it'd be 3 times 2. And then I'm going to do it again. Then I'm going to increase the bottom by 1. So it would now be a 3. So when I plug a 3 in, it would be 3 times 3. And then I would increase by 1 and I'd plug it in. So then it would be 3 times 4. And then I would stop because this 4 number on top is our stop number. This number right here is going to be my start number. I started with 2 and I'm going to keep going. What do I do with these 3 terms once I'm done? Add them up. I get 6 plus 9 plus 12. That is the answer to this question. That is what we're doing when we find the area under the curve, and I'll explain that here in a minute. Okay? That idea of sigma notation is what we are doing. Okay? We could have a fancy looking curve like this guy right here. And to find the area under the curve would be pretty difficult. All right? We are trying to find the best approximation for the area under the curve. We could use these big old wide triangles, okay? Or we could use a little bit smaller triangles. We could use midpoint. We could use left-handed Riemann sums, and so on. What would be the best size rectangle? If I want to be the most accurate, what would be the best thing to do with the area or with those rectangles? Make them the same width? I don't disagree with that. Make them really small. Good. Yes. So I found this website yesterday. I just thought of this right now that I'm going to talk about it. So imagine this shape right here. Okay, we got left Riemann sum. We got these rectangles are right here. How good of an approximation is that? Yeah, it's all right. Not great. Okay. What if instead of 4 subintervals, I used like 7? Is that better? What happened to the width of each rectangle? It got smaller because we took the same amount of space, but we made it smaller in between. Okay, what happens if I do that? Better. What happens if I do that? I mean, it's not perfect. I could zoom in and you can see, oh yeah, there is still a little bit over, but it almost looks perfect. Okay, you're covering that thing pretty close and you're just finding the area under the curve. The smaller those rectangles are, the better it's going to be. Everybody kind of agree with me on that? And so that's eventually what we're trying to do. All right, and so we are finding the sum of the rectangles, S sub n. That's what we're trying to do here. Find the sum of the rectangles. We're going to start at whatever our first rectangle is, and we're going to keep going until the last one. It's not real complicated. This right here, f of c, stands for the height of each rectangle, and delta x stands for the width. That's what we're doing. We're finding rectangles. We're finding a whole bunch of them. We're going to add them together. If we want to have the best answer, what do we want to be true about delta x, about the width of each rectangle? We want it to be smaller and smaller and smaller. Okay? So that right here, don't worry about this too much, but this is technically the best answer. Okay? We want to take the limit where they use this idea right there, but it's that this thing is approaching 0. Because if that width gets closer and closer to 0, we're going to be better off and we're going to find a better answer. Okay, we'll talk about this again in the future, but that's what we're going to do. We're going to add up all the rectangles, height times the width, where that width is as small as possible. An easier way to write that looks like this. Oh, okay, this integral sign that we've done. What does this number on bottom mean? That's the smallest number. That's our starting number. We're going to start at that bottom number. And we're going to keep finding the area under the curve until we get to that top number. That's our stop number. And then we are going to integrate the different areas. So whatever our shape is underneath, we're going to integrate those areas. And in the end, what are we going to do with all those different areas? Add them up. We're going to add them up. Look at this sign right here. That curly little S guy. Guess what that thing really started from? It stands for the what? Sigma, the sum. Okay, that sign right there is the idea of sigma or sum. We're taking all the numbers from the start to the end, and we're going to add them all up. That's where this thing comes from. Okay, I'll explore that again in a later lesson, but at least you've seen it. Okay, and we'll continue to do that from here. Let's do it. So today's lesson, not nearly that complicated. Okay, today's lesson is geometric area under the curve. Pretty straightforward. Find the value of the integration from 1 to 4 of 5 dx. Let's make a graph. We're going from 1 to 1, 2, 3, 4. Oh, I can't count to 4. That's 4. Show me with your arm. What's the graph of 5 going to look like? 1, 2, 3, 4, 5. There's 5. I'm going to make a graph. It looks like that. I'm finding the area under the curve starting at 1 and going until 4. That's this guy right here. So if I'm finding the area under the curve from 1 to 4 of 5, what's my answer going to be here? Ooh, I see all of us got the same answer at the same time. What shape is that? It's a rectangle. How do you find the area of a rectangle? What's the base? 3, what's the height? 3 times 5 tells me that the answer to this question is 15. Because that's the area under the curve. We just added these different rectangles. Now this one was easy because it was just one big rectangle. Okay, and it was a perfect fit. If you wanted to, if you draw your picture right, you can count the boxes. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14. Yay, it's 15. Make sense? It's easy. Let's go to the next one. Find the value of the integration from -2 to 2 of the square root of 4 minus x squared. Make this a little graph here. You wouldn't have to graph this thing, but it's always nice to see it. What shape am I making here if I'm graphing the square root of 4 minus x squared? Semicircle. We learned that in bell work today. So I'm starting here at -2. I'm drawing me a little semicircle the best I can do. Oh man, I was so close. It's almost perfect. Oh, now it's garbage, but that's okay. There's my shape. I'm finding the area under the curve, starting when? I'm starting at -2 because that's the lower part of my bounds. What's my upper bound? 2. So from -2 to 2, I'm finding this area under the curve right here. That's the goal. We could do some rectangles, but rectangles really don't make any sense here. What area should I find instead? Semicircle, correct. Area of a semicircle. Area of a circle is pi r squared. Hey, that is definitely a semicircle. Pi r squared. So what am I going to do here? It's pi times, what's my radius? 2 squared. What else do I need to do with that thing? Divided by 2. Cut it in half. Because it's a semicircle. It's not a full thing. So 1/2 pi r squared. So 1/2 pi times 2 squared. So 2 squared is 4. Cut that in half. It is 2 pi. That is the area under the curve. Okay? 2 pi. That's like 6.28. We can't count the boxes here, but 1, 2, 3, 4, 5, 6 with some little extra. Oh yeah, it's probably close to 6.28. We're just finding an area under the curve. Everybody good so far? Flip it over. On the back side, we are finding some values. Graph that one for me. Negative 1/2 x plus 4. Integrate it from 0 to 4. See what you get. Graph this thing. It is a line. It's got negative 1/2, so this is my what? That's my slope. Down 1 over 2, down 1 over 2, down 1 over 2, down 1 over 2. That goes to 8. Draw your line. 1, 2, 3, 4. If I'm finding area under the curve, when am I finding the area under the curve here? From when to when? 0 to 4. Not the whole thing. Okay? You don't always find the area of the whole thing. Normally you don't. Okay? In this case, we are going from 0 until 4. So I'm starting at 0, 1, 2, 3, 4, and I'm going till right there. So what shape did I end up with here? Trapezoid. You can find trapezoid area, whatever your favorite method is. You can split that up into a rectangle and a triangle. You can do the average of the two heights, whatever makes you happy. What would you like me to do? Trapezoid it is. So what is the height of this guy over here? 4. This guy's 4. This guy's 2. So we talked in bell work. You take the two heights, you add them up, cut them in half. What's the average between 4 and 2? That's going to get you 3 times the width. 1, 2, 3, 4. My answer, 12. You can do it that way. If that bothers you and you don't like what I just did, then do it this way. Here's a rectangle. Count them up. 1, 2, 3, 4, 5, 6, 7, 8. That area is 8. I've got a triangle. 1, 2. That's a half. I'm sorry, that's 1 because you got some halves in there. So that's 1 over here. That's 1. That's 1. That's 2. 8 plus 2 plus 1 plus 1. Whatever. Doesn't matter how you do it. Whatever makes you happy inside, find the area of that shape and you're good. Okay, our answer though was 12. Let's go to the next one. Find the value of the integral from 0 to 4 of x minus 2. Absolute value plus 2. Show me with your arms. What's that shape look like? Point. Which way does that minus 2 take you? Point. Which way does that plus 2 take you? Graph it. We get this shape right here. It's absolute value. This minus 2 took me to the right 2. This plus 2 took me up 2. Right 2, up 2. That's where I got that dot right there. I'm finding area under the curve since I'm doing integral. From when to when am I finding the area under the curve? 0 to 4. So I'm starting at 0. I'm going to until 4. It gets me this shape right here. Okay, it's kind of a funky shape. If it's a funky shape, you're not quite sure what to do, split it up. Okay, how could I split this thing up? 2 trapezoids. You could take it, cut it down the middle, make 2 trapezoids. Go for it if that's what you want to do. I'm going to split it up into a rectangle down here and then 2 triangles. So I got like this spot right here, a rectangle down there. What's the area of that guy going to be? 8. That one's easy. And then I got this little baby guy and then that little baby guy. How much are each one of those little baby guys? They're 2 because it's 1 and then 2 halves, 1 and then 2 halves. 8 plus 2 plus 2. My answer is 12. Doesn't matter how you find it. Add them up. Get an answer. Everybody okay with finding area under the curves? They're not that complicated. Draw good pictures. Anytime, and this is something I'm going to just tell you again. I've told you in the past. We are never going to be able to do this problem by hand. I am never going to teach you how to find the absolute value by hand, integral of that. It's complicated. Not something we want to do. If you get an absolute value problem in calculus, you should draw a picture of what that looks like. Okay, whether you're finding the slope, whether you're finding if it's continuous, whether you're finding a derivative, whether you're finding an integral, drawing a picture is going to be the easiest way to do that because absolute value is not that complicated, but the calculus behind it is. All right, so this is the problem I was telling you about earlier. I guarantee this is on the AP exam. I guarantee it's worth at least 2 points, if not more than that. Okay, let's look at what it says here. The graph of f of t is given. So this over here is a graph of f of t. And then they tell you that capital F of x is equal to the area under the curve starting at 0 and going to x of f of x. All right, this is the first time we've seen it, but just so we know, when you have f of x normally and you take the derivative of it, what do we call it? We would call it f prime. If you have f of x, and this is just the normal nomenclature they use, if you have f of x and you take the antiderivative, you do the integral of it, they will usually label that with capital F of x. That's kind of the opposite way. So if we have f and we go up, it becomes capital F. That's kind of what they're saying here. This is F. We are finding capital F, which is the area under the curve starting at 0 and going to X. So let's do that. Okay? If I'm doing the letter A and I'm finding capital F of 0, it tells you right here that capital F of 0 is going to be equal to the integral starting at 0 and going to whatever X value they say. So for letter A, what X value am I going to? 0, because it says right there, go to 0. So I'm going from 0 to 0. This F of t dt, nothing changes there. Because they didn't tell me a t value, they told me an x value. Okay? So I am finding, in other words, the area under the curve starting at 0 and going to 0 of that function. So let's go over here. Here's 0 right here. Ready? I'm going to move to 0. Start at 0 and I'm going to go to 0. How much area is under the curve if I start at 0 and I go to 0? 0. No, I didn't move. Okay, if I didn't move, you're not going to have any area under the curve. The answer is 0. If your upper and lower bound are the same, it's always 0. Okay, letter B. We're finding the area under the curve because we're finding capital F. That's this guy right here. We're starting at 0 and we're going to go until 2. Because our x value is 2, I'm plugging an x value in right there of F of t dt. So on this graph right here, I'm starting at 0. And I'm going to find the area under the curve until I get to 2, to right there. I want to find that area under the curve. It doesn't matter how you do it. Okay, you can do some trapezoids. I would suggest just doing rectangle and a triangle. What's the area of this rectangle right here? 2. The area of that triangle? 1. Because the base is 1, the height is 2, and then you cut it in half, so it'd be 1. So what is the integral from 0 to 2 going to get me? It's 3. All we do is we add those up. 1 plus 2. We're doing the summation. Okay, we're taking the areas and we're adding them up. It's 3. My next one. I'm finding the area under the curve. I'm going from 0 until 4 of F of t dt. All right, so 0. I'm going to go until 4, so that means that I got to go to 3, and it's the area here. It's that area between the x-axis and the curve, so I get that thing right there. Okay? What do you think? What is the area of that first pink triangle? 1. The area of the other one is 1. What do you guess? Just use your brain. What do you think I'm going to do with that triangle that's below the x-axis? I'm subtracting. Okay? If it's below the x-axis, we are subtracting. Okay? Because it's not a positive value or not a positive area, it's negative. So we're doing 1 plus 2 plus 1 minus 1. So the two pink triangles, guess what they do? They cancel. And so the answer to this question is also 3. Because all we did is we added a triangle 1 and then we subtracted it. So it didn't change the area from the previous answer. Make sense on that one? Try F of 6, see what you get. We're integrating from 0 to 6. So we're finding this area right here. Okay, so this guy right here is going to be 2. This guy right here is 1, and that guy right there is a half. So it's, or in other words, 1.5. So we're taking this area that we had from this last answer of 3. We're going to subtract 2 because it's below, and then subtract 1.5 as well. And so my answer here is -1/2. Oh, -1/2. Kind of makes sense? A little bit funky. Let's do this last one. I'm going to do it really quickly. Okay? This last one. Same setup. Everything's the same, but now g of x is equal to that. What is different about g of x compared to what f of x was? It starts at 2. So we're starting at 2 on this first one. We're going until 0. So we're starting here. This is my start line. And I'm going backwards to 0. And he guesses. So this area we said was 2. This area from above we said was 1. Anyone have a guess as to what they think the answer to capital G of 0 is going to be? It is -3 because we're going backwards. We always put the bigger number on top. Oh no, they screwed it up. So it's really like we're going backwards. Okay, we're finding negative area there. Letter B, we're going to g of 2. So we're starting at 2 and we're going until 2. What's that area going to be? It's 0 because you started and ended in the same spot. Try that last. Look at it. We're integrating this thing from 2 to 6. So this area is 1. This area is negative, or not, I don't want to call it negative 1. 1, 2, and 1.5. So it's 1 minus 1, minus 2, minus 1.5. Those two things are canceled. Negative 2 minus 1.5. F of t dt is going to be negative 3. No, just plain. Negative 3.5. Sorry.